give you a brief intro to Dr. Okon. So Dr. Okon is an engineer with over 20 years experience in electromagnetic modeling and antenna design. He holds a BSc and an MSc in electrical engineering from the University of Lagos and a PhD in electronic engineering from King's College University, London, focused on antennas. After King's, Ernest worked for BAE Systems for approximately 7 years. Then he moved on to Thales, where he's worked up till now as a specialist, all focusing on the area of antennas. I think he's in a very good position to speak to us today and present on antennas, and I look forward to the talk. I'll now hand you over to Dr. Okon.
Okay, so this talk today is on antennas in wireless communication and sensor systems. It's a general history of antennas, and the perspective is entirely mine. I will try to place you in the perspective of what the antenna engineer goes through in all respects. So the contents of this talk will be as follows. There'll be an introduction, a history, I'll give you some antenna types generally, and some modeling, some areas of application in industry. There's propagation, some areas of emerging technology, materials and manufacturing, and particularly mobile phone antennas, which I know we all use, and it's something I like to highlight in talks of this nature. And there's some challenges and there's some. So basically, the antenna is a transition device between a free space wave and a guided wave. It's as simple as that. Radiation is realized by the acceleration of charges on structures. So once you accelerate charges on structures, you get radiation, and that's been well documented over years. Progress in antennas has been on for over 130 years. It began in 1886, but its origins are obviously much older in electromagnetic research. And antenna is obviously a key component for wireless communication and sensor systems. The application is pervasive throughout life in air, land, sea, and space platforms. So to put you in the mood, historically, there's been a lot of men and women who've made significant contributions to this field, and I can only provide a few names that signify milestones. Of course, these names have been significant contributors to the technology, no doubt. So I'll start by saying that Thales of Miletus, the name is Thales of Miletus, was a Greek philosopher who did a lot of work. It is not known if any of his writings have survived, but his findings and work were passed down through the ancients. And so the work he did on electricity was essentially what we now know as electrostatics, where you rub an amber rod with a silk cloth, you attract fluff, and obviously that's something we can always replicate now at home. The magnetism part, he discovered some stones in a place called Magnesia, lodestone, as we were called then. Magnesia is a small town in Greece. From the name, we get magnetism. From amber, the Greek word, electron, electricity. So those were the starting points for that work. But it wasn't until 1600 AD, which is over 1,000 years after that, William Gilbert of Colchester, England, published his great book, The Magneta, in 6 volumes, where he places in context findings on electricity and magnetism, things like the Earth being a giant magnet, and the apparatus he developed called the electroscope. So the context is set for electricity and magnetism, but they are still 2 separate subjects. By 1850, you have Benjamin Franklin, the lightning rod. Franklin is a US statesman and founding father of modern America. But but he's done some very interesting work on the lightning rod. He's coined the convention positive and negative charges, and he's also done some work on the conservation of charge. So the technology is developing quickly now in this era. By 1785, you now have Charles Augustus de Coulomb, the French engineer, being able to categorize forces between charges and magnets. So he develops a torsion balance, and he can quantify the electric force between charges and magnets. Now, the turning point for theoretical studies is done by C.F. Gauss. But prior to Gauss, Lagrange had done some work before that in 1773, where he's talked about Gauss's law, what we now know as Gauss's law. But it was Gauss who put it in a more firm footing. He talks about the charge contained in a volume being equivalent to the flux emanating from that volume. So that's a very important law. But the real turning point for practical work from electromagnetism has come in 1800 with Volta's Voltaic pile. The pile provides a source where people can use to do experiments, and the experiments follow very quickly. By 1819, we all know Hertz and Ørsted's work at electricity produces magnetism, and by 1831, Michael Faraday, the eminent physics chemist at the Royal Institution, has done experiments to show that magnetism produces electricity, which is obviously the Faraday's law of induction, electromagnetic induction. So by 1831, people are beginning to ask the question, is electricity related to magnetism? And then the terminology electromagnetism begins to be used. 1840, big turning point in history. The telegraph is invented by a collection of people, Joseph Henry, Morse, Samuel Morse, of course, the code, and Charles Wheatstone in London. So we get to 1873, and this is the spark where Maxwell provides his equations. The equations are developed over a period of about 9 years, from 1864 to 1873, where he publishes his book on magnetism, electromagnetism, and so everything is now in place to actually do a practical demonstration. And that's left to Heinrich Hertz, who demonstrates the first radio system, in a sense. He's posed a question by his supervisors, Gustav Kirchhoff and Hermann von Helmholtz: can you make an experiment to demonstrate Maxwell's equations? And it's taken a while, but by 1886, he demonstrates this to the Berlin Academy of Sciences to obtain the Berlin Prize. So we have all this in place. And Hertz is asked the question at that time, do you see any practical use of this? And he says, not really. And that's what a scientist would say. He would say. But Marconi is the man to really commercialize the concept of radio and the antenna. He comes to the UK in 1896, and he takes out a patent for his radio transmitter he's been developing. 1901, like I said here, he does the Atlantic transmission. 1909, he wins the Nobel Prize, which he shares with Karl Braun for his work on wireless telegraphy. 1912, he puts his kit on ships, thanks to Lloyd's of London. 1912 is the Titanic. Titanic sinks in 1912. The Marconi kits are on the Titanic. It's a very sad epoch in history, but the general public accepts that Marconi's wireless kits on the Titanic has helped to save a lot of lives. 1915, Marconi now begins to accept that he has to make use of more innovative equipment to do much more than wireless telegraphy. And by 1920, he begins broadcast from his office in Chelmsford. By 1922, the BBC is formed from a collection of radio amateurs in the UK. The Marconi Company is in the forefront of that. So that's the general history of where we are. And I'm now going to talk about the antennas in particular, which forms part of the radio set. So following Maxwell's innovative work, where he shows that light is an electromagnetic wave, there is now the acceptance that in the spectrum, you can generate an electromagnetic wave across that spectrum. At least you see from the plot here that light is just a small sliver of that spectrum, but radio waves are on the right-hand side. It's important to emphasize this because radio waves are what we call non-ionizing radiation. On the left-hand side, it becomes ionizing, and that is not very healthy over long exposure times. But the basic field wave for the electromagnetic wave is a transverse wave. The E and H fields are orthogonal to the region of transmission, and this is what it looks like in the far field. In the near field, of course, things are a bit more complex, but I won't discuss that right now. Here is an illustration of the apparatus used by Hertz in his 1887 apparatus. Now, if you look very carefully, there are two antennas. He's used what is called a dipole antenna. It's a horizontal dipole, and it's used a loop. He's generated a spark across a room using what we call a spark gap transmitter. The spark gap transmitter is the first radio transmitter. The dipole antenna, what Hertz has reported, is essentially half a wavelength dipole with loaded ends to provide you with a resonance at the frequency, which is usually roughly about 50 megahertz. So this is the apparatus Hertz has used. It's outstanding at that time. And what Marconi does is that he takes this equipment and he begins to tinker with this. What he comes up with in 1901 is what you see here. So in 1901, Marconi provides this, and this is taken for him about 6 years of a lot of tests across the UK where he does this Atlantic transmission. This is the big transmission across the Atlantic. The antenna there you see, it's held by 4 poles. As you can see, that antenna is called a monocone antenna. It's half of a bicone. The patent belongs to Marconi, which he took out in 1896. It's a classic antenna. It's now known as the Marconi antenna, but I would say that it was very innovative for its day. It provides you with what we call an omnidirectional pattern. So it's broadcasting all around, but Marconi is fortunate because he picks the right frequency to make this happen. Many people believe this would not happen, but I would say he picks the right frequency, and I will discuss a bit more of that later when we get to propagation. So the radio systems people quickly realized that they need to be able to transmit and broadcast the signals. And so a few challenges immediately become apparent. Once the size and mobility of the kit you're using at low frequencies, things become very big, as you know. The frequency is important. You have to transmit the distance and the capacity of where you're transmitting to. How many people are you transmitting to or broadcasting to? And power and efficiency of your kit is important. I want to emphasize that the Marconi kit was essentially what we call today small antenna. Small for the frequency it was operating at, which means that it wasn't very efficient. But like I said, he was very, very fortunate to make use of the environment of propagation at that frequency. Now, so a link budget is necessary to evaluate signal to noise ratio, and antenna performance and cost impacts all of them. So this is basic antenna characteristics, which is very well known for people who do antenna work or otherwise in this field. We have a pattern, which is what the antenna radiates, and we try to control that pattern by varying amplitude phase polarizations. That gives us the main beam and sideward levels. And the key here is how do you design your pattern to either make use of the whole aperture you have to give you a higher gain, or do you go for very low sideward levels if you want to minimize interference, or you trade that with aperture efficiency. So it's a trade-off of what you want to do. It's a designer trade-off. The input match is also important, as I indicate there. And the pattern I showed there on the bottom is a 3D pattern of an omnidirectional antenna. The Marconi pattern of 1901 will be somewhat like this, but it's a monocone, so it will be half of this donut. So you can imagine half a slice of through that pattern along its horizon. So some basic equations for antennas. In general, the antenna designer makes use of Maxwell's equations. That's the general norm now. These equations are on the top there. The 4 equations of Maxwell have been put in a more concise form by his successors, the likes of Oliver Heaviside and co. The radiated field is deduced from Maxwell's equations. And what we have is, and the field comes through what we call a potential expression for an antenna in free space or in complex media. So the last equation on the bottom there is the potential expression. It's more or less an integration of the current distribution with the Green's function, what we call the Green's function. In free space, it's fairly close form. For non-free space situations, it's much more complex. The antenna equation can be placed in a more compact form with the use of advanced mathematics, basically function analysis. We can say an operator on the current distribution gives you an output. J usually is the current distribution of the antenna. Once you know the distribution of the antenna and its current distribution, then you can actually predict its performance, its radiation pattern. So all the work that has been done for modeling in the past has been to try to decipher what the distribution of the current distribution on the antenna is. So the typical case is that you have the antenna, which is L, G is your source, and your response is J. In some cases, you want to do what we call antenna synthesis. In that case, you have an idea of your current distribution, an idea of your far field pattern, and you want an antenna to fit that, and that's what we call synthesis. Otherwise, it's an analysis problem of finding J. Now, let's talk about antenna modeling, the progress, very briefly. I would say that the progress in antenna modeling has been very impressive over the past 130 years, especially from 1890. After the Hertz experiment, people have found equations to describe current distributions. So the work of Pocklington and Hallen, Fredholm and Keller provide closed form expressions of what an antenna distribution looks like for an antenna and then pattern. But from 1960 onwards, something happens where people begin to look at matrix techniques. And so the works of method of moments, Harrington, Richmond, finite elements by Zenkowicz and Taflop, they have introduced the matrix method. What this does is that it opens a whole new dimension to modeling. You can predict performance of very complex structures. And these techniques are techniques we use in industry today. 1990s onwards, you've had large-scale parallel computers making use of these models, these matrix techniques. So we can actually model very large structures with very large computing resources. So basic antenna types as follows. So the Y antenna, the dipole antenna is the antenna similar to what Heinrich Hertz has used in his experiments. It's one of the most common antennas. The pattern is, like I said, is donut, the omnidirectional pattern I showed earlier on. The monopole antenna is also another Y antenna. So Y antennas are the first main antennas we use for antenna work. When we get to 1926, something really impressive happens. You have the Yagi-Uda array. It's come from Messrs. Yagi and Uda in Japan at the Tohoku University. They have developed what I would say is a classic TV area, which is what everyone has grown up with in the past, the TV area before DBS, of course. And the Yagi-Uda array is now, well, it's commonplace. It's one of the most iconic antennas. The LPDA on the right, on the bottom right, is also a variant, but it's more broadband. So these are Y antennas, and this is what the whole world has generally accepted as antennas in this area, of this range. Here's a classic antenna, or antenna array, so to speak. This is the last chain home radar radar tower standing in the UK today. It's a Great Barlow in Chelmsford. And this was designed by the Marconi Company prior to World War II, used on the southern east coast of the UK, and essentially a classic. It's a British landmark, and rightfully so, because it's quite an impressive antenna in many respects. So further to antenna type, to look at the aperture antenna. Aperture antenna has been developed over a number of years. I would emphasize that it's made possible because you can propagate waves largely through waveguides, and this was a very important technology. It was first demonstrated by Lord Rayleigh in 1897, where he uses mathematical techniques to show that you could propagate waves through a hollow tube. But Chandra Bose in India has shown in 1897 also that he could conduct tests using aperture antennas. So aperture antennas, the reflector antenna is the classic dish antenna, we call it. It's used for home broadcasting. The horn antenna is used sometimes as a feed to a reflector, but on its own is an antenna. We have dielectric structures, aperture antennas, and then the solid array is another type. So these are the type of antennas that are generally in use. Here's another classic national landmark. This is the Holmdel horn, developed by Bell Labs in the 60s for observing satellites. So it was developed by Bell Labs. It's a classic device because it's unusual. Unusual because it's a composite structure of a horn and a reflector. So the horn, if you look from the left-hand side on the portal cabin, that's the horn coming into a reflector. And it's a classic antenna because it has very low sidewalk levels, a good aperture efficiency, and it can be used to observe space. It can be used to observe space. So this antenna is used to observe the first satellites launched by Bell Labs. But by 1865, it has another use. Arno Penzias and Robert Wilson have used this to observe background cosmic radiation, and for which they deduce a value of 3 degrees Kelvin. And that's what we have come down to, if the world has now accepted as what is background radiation. They shared in 1978 Nobel Prize for Physics for this impressive work. But the antenna on its own is an impressive piece of equipment. So we fast forward more recent times, the 1960s, so 60s and 70s, the printed antenna is developed. Initially, the microstrip work is done by ITT in the US, but the microstrip antenna becomes more of an industry equipment from the 70s onwards at lower frequencies. A lot of work has been done. A lot of people have made contributions to this structure. It's fairly low profile. It's easy to manufacture using photolithographic processes, and it is fairly low cost. So this is an attractive option. It's printed on substrates. A lot of work over the past decades have shown the type of structures to print it on, and the types of performance have been varied and very useful. Now we come to phased arrays. Phased array is what I would call is the rave of, it has been the rave of the moment for decades. Carl Ferdinand Braun in the 1890s has made claim to have invented the phased array. And that is a very plausible thing, because in his Nobel Prize lecture of 1909, he talks about this concept of the phased array. But the phased array essentially is an array where you can vary each element in amplitude and phase to steer a beam from a fixed aperture. It's an object of attraction even today, and it's a most challenging problem to solve in many respects. But here's just a picture of what a phased array could do. The opportunities for phased array are huge. So we now look at applications of antennas, and a few applications here. Weather radar. On an airport, you tend to have weather radars. You have antenna radars for aircraft surveillance, and these are parabolic antennas. You can see dishes. You have man-pack radars which you can carry, and you have body-worn antennas now which are emerging, where people can actually have an antenna etched onto clothing, as we say, body-worn structures. Antennas on aircrafts are huge. This is an example of the Boeing 787, where its antennas have been published by the Boeing company. There is a plethora of antennas on this structure, as you can see. And the modern aircrafts need this to provide information for safety. Things like how you're traveling, how fast you're traveling, what the weather is in front of you, the landing processes using the VOR, so LOC capture. So a plethora of antennas on the aircraft, and the whole objective here is to provide information more so to the pilots, operators, and nowadays to you, as you can see on the screen underneath. Antennas for airborne platform continues here. You have antennas on fighter jets, and it's mostly phased arrays these days, and antennas on UAVs are commonplace. And these antennas are of various types or various. On naval platforms, you have antennas, and as you can see from the diagram on the bottom here, it's not just having an antenna on the platform. The question is, how do you model the antenna to make sure that the antenna is placed in the right place on the platform? Because an antenna not in the right place, obviously, will not function as well as you have designed it. So antennas for space applications. So you have antennas on satellites. Inmarsat 5 is a clear case of where a lot of antennas were placed on the satellite to provide coverage for maritime operations. And I want to emphasize that it's not just the antenna on the aircraft, it's the control mechanism for antennas. So the plethora of antennas sit under the aircraft to make the space on the satellite to make sure that you get coverage from satellites. The ground stations are indicative. You need to communicate. Again, it's an issue of making sure your link budget is right, and the antenna patterns on the earth, or in this case, will be adequate to provide coverage you want. So antennas are everywhere, including space. Here is an antenna application on Mars. Here you have the Mars rover. The Mars rover is a probe that went to Mars in 2011. It sits with two antennas, and these antennas, the functions as follows. So you have the two antennas that can communicate both with the orbiter orbiting Mars and with the ground station somewhere, perhaps the Jodrell Bank station on the ground in Cheshire, or the NASA Deep Space Network. And these antennas, usually what we tend to do is to have a UHF antenna communicating with the orbiter and an X-band antenna that can go further and communicate. Bear in mind, in the case of Mars, you're somewhere between 60 million kilometers to 250 million kilometers away from the Earth. So it takes some time, somewhere from between 3 and 11 minutes for the signals to propagate across space to be reached. But this is the kind of setup you have. This has been a very successful mission. Here's a classic case of a mission I got involved with in 2007. We all know that the Beagle 2 program didn't go entirely as planned. Beagle 2 was a probe that was meant to have made descent into Mars on Christmas Day 2003. It didn't happen, but ESA has done a post-mortem of this. I was involved with this, where we showed clearly that the antenna, which you can see in the Beagle 2 prototype there, it's the slot antenna in gold there, and there was no link once the spacecraft, the probe left the orbiter, because the antenna was within the clamshell. So what we involved with ESA was to design something that would prevent this in the future. And what we came up with was an antenna on the parachute, which you could etch on the parachute, a Fresnel lens antenna. And that has been a signpost to show that antennas are also important, and you must get it right, even on space missions. Very critical component for communicating. I just want to emphasize something, and I'm going into propagation here, is that when we propagate signals through the atmosphere for antenna work, we have to have an idea of what the propagation environment is. So here's a clear case whereby there's a push these days to go into higher and higher frequencies. And you can see from this attenuation charts here that as you go into higher frequencies, the attenuation increases. And this is important. So say at 60 gigahertz, you have a huge absorption of the atmosphere due to oxygen. It's a resonant frequency of oxygen. And the same thing at 119 or 183 gigahertz. So these are peaks you have to be sure you know what you want to do with. It doesn't mean you can't work on these frequencies, but you must know what you want to work with these frequencies to do. Most people usually work in the troughs where there isn't a peak, and those are windows, we call them, and those windows are useful for propagating signals. This is a chart of what propagation environment looks like at radio frequencies. Between 3 kilohertz and 300 kilohertz, you have what is called a ground wave. So it's fairly low frequency. Low frequency propagation is on the ground. And between 300 kilohertz and 300 megahertz, or 330 megahertz, you have propagation skywave. It's important because 30 megahertz is the HF band. When Marconi did his transmission, I said he made use of some fortunate circumstances in the environment. And one of that was that people did not believe you could transmit across the Atlantic over such a distance. But what Marconi was able to show was that he could do that because he made use of the ionosphere, the bounds of the ionosphere. He was propagating at a medium wave frequency, and that frequency band makes use of the skywave to reflect the signals off. At the time, he wouldn't have known that, and at that time, many people didn't know that. We had to wait until 1926 when Appleton and Co. were able to show that the ionosphere was indeed responsible for bouncing radio waves up. And since then, it's been a workhorse, gold horse for radio wave broadcast. The urban environment is also important. Here you have below that the chart that shows what you need to do to propagate in a mobile phone scenario. Clear case whereby mobile phone designers will have to make use of cell planning to make sure that various base stations are situated accordingly to give you a reception. Sometimes when you don't get reception, the problem is that you are outside the cell area. Of course, we know that, but the fact is cell planning is important. Propagation studies are important to place the antenna towers and the mobile handsets. And this continues with indoor modeling, developed modeling. And all this modeling is done with the use of the equations I had pointed out earlier on. So modern techniques give you a good idea of what you can model. Like I mentioned earlier on, install antenna performance is important. It's not just placing an antenna on the platform. You have to know what it does for many reasons, but to mitigate cosine interference, improve EMC, radiation hazards and compliance must be adhered to. So these are things we take into consideration in designing antennas on platforms. So I'll just give you a rundown of some emerging technologies. Some of these technologies have been around for a few years now, and they're being deployed. But a lot of them are still not fully mature, but they are coming on stream. And now with the advent of 5G, you will see more of these technologies in use. I have highlighted this in the past. I did a different talk, but I will highlight it now. And the application, of course, is for wireless communication and sensor systems. So MIMO is multiple input, multiple outputs. What this means is that you have multiple antennas on transmit and receive. The objective is to improve reliability, aid diversity. In a case whereby you're transmitting the same signal across all multiple antennas, you're improving reliability and you're aiding diversity. Another way of doing this, obviously, is to improve capacity, where you're trying to boost your capacity over an enclosure or an environment. But most people use this for improving antenna diversity and reliability. So some micro antennas you may see around the home or in the vicinity of your home are things like Wi-Fi, where we have nowadays multiple antennas on a Wi-Fi kit. It's all about reliability. And on the base station, you have that. Another topic is smart antennas, adaptive antennas. These antenna types are coming on stream. And I'll give an example. So it could be a phased array, it could be just a switch beam antenna, but the whole idea is that you have a dynamic pattern. And if you look on this chart, you see whereby typical base stations these days are just static beacons they generate in this situation. But if you imagine yourself, say, in a loud crowded environment, say a football game, where there is a need for people to communicate very quickly, maybe due to some unforeseen circumstances. Everyone picks up their mobile phone and they make a phone call. What you'll find out is that the system will eventually crash because of capacity. You overload the system. But with a dynamic antenna, you can do what you see on the right-hand side is that you can beam for such that cell areas that are in big need of capacity can be given capacity by neighboring cell areas. And this is a common area for mobile technology and for all types of communication, including sensor systems. UWB is an area I've been involved with for years. It's all about bringing back pulse transmission in the civil domain, but it's very low signal. So it's a cable replacement technology. The future is that you want to get rid of cables entirely, and you want to transmit wirelessly for things in the home, for things around the home. And with ultra wideband technology, you can do that, a bit with some caution. So if you see the chart on the left-hand side here, the signal level for UWB is very low. So that allows you to transmit pulses over broad bandwidths and frequencies without interfering with general mobile phone 2G or 3G networks. Here's a UWB antenna, handheld. It's essentially what it is, a spiral antenna printed, and it can be very broadband. Millimeter wave work is here. It has come on. This is something that was speculated 20 years ago, and it is here now in terms of automotive radar for cars, vehicle-to-vehicle communication. The technology has been in development for over 20 years. And this is an example of an antenna that we use in that area. It's a printed antenna. Printed antennas in the past didn't work very well at very high frequencies, but we've been able to get them to work, and it's good to see this technology coming on stream. Another area is terahertz. In terahertz range, you have applications for things like medical imaging, imaging of, say, dental imaging of the teeth. It's very short range, as you can imagine, because propagation losses are huge, but there's a huge area of application for things like this and for surveillance. Mesh networks are networks that are very important, and they are coming on stream, and they've been on stream. The whole idea is that you have a locality that you can seed. Here's a picture representation whereby you are able to use everybody else's node to communicate in a locality. It could be in a home or home to home. It could be for roadside beacons on the highway. But mesh networks are important, and this is where we see a lot of antenna work being developed. Ad hoc networks are somewhat like mesh network, but they're not. They're more peer-to-peer, flat, non-hierarchical. I mean, ad hoc networks, everything is mobile. And this is an area that, yeah, we're seeing more application. We will see more application as we go ahead. So here is the one of the most important emerging technologies where you have something, we call it orbital angular momentum. But the whole idea is that people have now found that you can twist radio waves, and you can generate a series of orthogonal waves that do not interfere with each other. What this means is that from a transmitter, you can transmit several modes of orthogonal transmission, or we call vortex beams. And with OOM techniques, you can significantly increase capacity. The capacity being touted is about 100 gigabits per second by entity, and this kind of application will be possible from about 2030 onwards. It's a big area, and an area which I think is going to come on stream. So I look at a few materials, metamaterials. So metamaterials have been talked about and been touted for a few years now, over a decade. Essentially, they are non-naturally occurring materials, and they provide very novel properties. If you look on the left-hand side, you see two glasses. One, which is what you normally would observe optically, is positive refraction, which is what you would see through a glass or a lens or prism. What you see on the left-hand side of that, the second glass towards the right, is negative refraction. And this is not an occurrence that occurs naturally, but thanks to a lot of innovation in the UK, US, and elsewhere, people have been able to develop metamaterials to provide novel properties that are not in existence. These kind of materials are very useful for making compact antenna structures. And it's an area that is very fertile and is still in development. So you imagine area more or less. And the follow-on from this is nanomaterials. This is the high point of today's technology, where you can synthesize any type of material in 2 dimensions or 3 dimensions with the use of artificial intelligence and machine learning. So you feed into the computer the traits of the characteristics of the materials you want, and what type of properties you want the materials to have, and it comes up with something really novel. And then you can try and realize this practically, and it is possible. And this is an area that is very fertile and in use right now. So manufacturing, 3D printing. 3D printing is coming upstream. It's an area that is now seeing more access for prototyping materials. And it's an area that the whole world is actually following very keenly. But it involves printing to a layered process using computer digitization. Lastly, I will just highlight mobile phones for you, and I'll say a few things. We are now in the era of 5G, and that's an area that is being actively developed. And the antennas being used are also being developed. So in the 80s, you had antennas like that mobile phone you see there, 87. And suddenly those kind of antennas have disappeared. Nobody wants to see them anymore. And that's rightfully so, because there are a few things, one of which is the issue of radiation to the body. Another thing is the issue of convenience. So modern mobile phones don't have dipole, monopole antennas. It's monopole antenna. You see there, they have printed antennas in the casing. And they become equally as good. So it's a good thing that technology is advancing, and this is an area that is being researched every day. I'll just conclude with a few things. The issue of health concerns on radiation, like I mentioned earlier on, is radiation is non-ionizing, and in the UK, there are regulations to make sure that mobile phone suppliers adhere to this. And we should all be careful of long-term exposure to radio waves, of course. Here's a way in which measurements are done for SAR measurements in the mobile sector, and mobile phone companies must make sure that the phones they make comply to SAR ratings. In the UK, it's 2 watts per kilograms in every 10 grams of tissue. So challenges for antenna design going forward, it's always the issue of cost and in the design, the size and compartment. Compactness is important, the weight, efficiency and power, of course. And for modeling, we need to build better models. The models we have now are very adequate, but to model complex materials is an area that is often challenging. So we have presented a historical perspective of antennas, the importance of antennas in wireless communication we've highlighted, and we've looked at the future area of sensors, and this is an area where there will be new innovations to meet demands for information and connectivity. I want to acknowledge a few companies, my company, BAE Systems, which I worked with previously, and a few colleagues in academia, and Dr. Nixon. Thank you very much. Thank you for listening. So questions?
Well, thanks very much, Ernest. That was very interesting. So we've got a few questions here, some of them. First, we have a question from A. Andolo. So he asks, the human body antenna and other wearable ones, how far are they? And I have not seen much of them lately in the research papers. So
yes,
I'm not sure.
Thank you for that question. A lot of work has been done in this area. And initially, when the antennas were being developed, there was a problem of interaction with the body. That has been largely solved from the point of view that you can actually screen the antenna from the body. But when you do that, you tend to you're limited antenna performance in terms of bandwidth and other traits. But this area is actively in production in different industries. So it is an area that's ongoing. I understand that it's not as widely reported, but I would emphasize that it's an area that's been researched. Yeah.
Sorry. We have another question here by Andrew Lavey. What is happening with Bluetooth and Wi-Fi antenna applications? This question.
Okay. Well, Bluetooth is, as you know, it was 2.4, now it goes to 5 gigahertz. Bluetooth 5.0 is one of the latest technologies, and the antenna work in that area. I would say it has sort of plateaued in the sense that the antennas are there for Bluetooth to Bluetooth work, but in order to push that technology forward, you have to demand more from them, from the antenna designer. Either you demand going to higher frequencies or you demand more capacity. But the antennas for Bluetooth work are there. They have been developed over the past 2 decades, and they're available. Like I highlighted UWB, and that's an area I think it will take up more interest.
And this question is from Kelvin. He asks, will the 5G phones have different, I guess, antennas compared to 4G phones? And in addition to this, if 5G becomes prevalent, will the 1G to 4G frequencies become obsolete?
Okay. 5G phones will be different from 4G. So 5G antennas will be different from 4G antennas because the frequencies of operation are different. So with 5G, you're going higher in frequency from 3 gigahertz to about 6 gigahertz in the lower band, and you're working at the millimeter wave band in some countries. Now, companies like Samsung have already developed antennas for that. But like this, the technology is available, but the antennas will be different. Now, on the issue of obsolescence, it wouldn't happen because there is what we call in the mobile sector, what we call evolution. So evolution means that the frequency bands are still available for use. The advantage of working at lower frequencies, which is what 4G is in this case, is that you get more penetration in propagation. What this means is that you may require less number of cell sites or base stations as against 5G where you require more. So nothing goes obsolete in this case.
Okay. We have a question here from Gabriel Pulneta. I may have pronounced the surname incorrectly. Apologies. What can you tell us about the challenge of protecting antennas against vandalism?
Good question. Well, to start with, antennas have to be exposed. There's not much you can do about it. Okay. Its question then now is twofold. I would say you address this problem in twofold. The first thing is that the public must be educated as to why antennas exist in the 5G world and what they do. I want to emphasize this point because it's not just for mobile phone use. These mobile networks provide emergency services. So I would say twofold. Public must be educated more. And two, build them higher up if you can. So much more you can do.
Okay, so here's a question from Pradeep Agarwal. Yes, apart from diversity, multiple input, multiple output antennas also used for beamforming, perhaps for 5G?
Yes, with 5G, there's been a talk of massive MIMO. That's the topic. So massive MIMO is a case whereby you're using it for huge data transmission over a large scale. That's something that 5G is proposing because 5G is planning to emphasize machine-to-machine communication with huge data rates. The second thing is the issue of ultra-low latency applications in 5G. And the third one, of course, is the issue of you want higher data rate. And MIMO can be used to provide that data rate. So yes, massive MIMO is what started with 5G.
Okay. And this question is from Mike B. Hold on. We have found a simple quarter wave wire antenna most effective with LP1. How might we determine that a coiled one would be more effective at transmit versus receive?
Well, the only way you can actually determine is twofold. You can actually measure the antenna efficiency. There are ways of doing that these days. There are many techniques you can use to measure antenna efficiency. And the second thing, obviously, is to determine the quality of your transmission and reception. So the gain is an indicative factor of how good an antenna is. If you have a good high gain, then you know that the antenna is working as well as you would like. So those are basic ways of determining performance.
Okay. And this is from Rajit. Are there any advancements in NFC? You may want to explain what NFC is to the group, I guess.
Well, yeah, so NFC is near field communication. Yes, 10 years ago, I would have put it on my list. Today, I wouldn't, because technology is fairly mature. There haven't been any major advances because we don't see the need to. NFC is essentially used for things like as a card reader, where you place a card next to a reader to be able to read your. Well, it's used on mobile phones, of course, but so it's essentially it's near field. The only way you would see advancement is if the demand for more data comes up. And like I said, there are other technologies that can do that, like UWB. So NFC, yeah, it's here, but I don't see any big push.
This is from an anonymous attendee. What are the biggest threats to 5G technology and its users?
Well, I wouldn't call it threats, but I would say they're challenges. Okay, 5G promises a lot in the sense that you have not put an upper bound on data rate. You say as much data as you can transmit, and there will have to be at some point in time some cap. Two is that in the millimeter wave region, like I showed from my chart on propagation, there are challenges. The attenuation levels are higher, which would mean that you may need more base stations than you have now. So those are the challenges I see for 5G going forward. Is the millimeter wave aspect of it and the demand for data. So we'll see how this technology evolves before we decide how we can improve it.
And this is another question from Ayandolo. What are the EMC challenges facing 5G antennas and standards? And the standards, I guess, related to 5G. That's what he's asking.
Yes. Well, the challenge I've already highlighted the issue of the demand for data rate. The other thing now comes into the issue of frequency spectrum and allocation. Usually countries allocate frequency spectrums and then decide and then give it out to people to use. I will say this, what we saw with 3G, where spectrum was sold and there was a push for lower frequency. This is what the issue is. If you have the lower frequency, you have more of the penetration. If you have the higher frequency, then you have to be more innovative. And that is the fact here with any technology. So with 5G, I would say the big challenge is in the millimeter wave region. And I'll give you an example. If you have a millimeter wave signal, it doesn't penetrate into buildings very well. So whilst you will have a TV area in the basement, you can watch TV with the TV area in the basement. If you have a mobile phone, even with 4G today, you struggle. So the big issue is penetration to buildings and to spaces. And that is the big challenge for higher frequency usage, which is what 5G will face.
And this question is from Phil Jones. Are multiple input, multiple output antennas practical on a handheld mobile device? Is there enough space? Does it mean physical? I guess physical space, yes. think that's the question.
It's a very good question. And I would say that, yes, it is possible. It is possible, but that is a challenge for the antenna designer. What we're looking at here is multiple elements. Now it becomes easier at higher frequency. So a millimeter wave, yes, it's easier. Lower frequencies in the 6 gigahertz range, it's a big challenge. But again, that's the challenge for the antenna design. So it is possible, yes, but we will have to be innovative to achieve that requirement.
Okay. This question is from DRC. This is initials. Do you foresee a reliable method for translating near field characteristics, to far field characteristics for an antenna structure and vice versa?
Okay. Yes, there are techniques to do that already, but it's an area for active research. In the past, people only worried about the far field of an antenna. They didn't worry about the near field. But in today's world, people are interacting closely with the antenna, so the near field becomes an issue. The near field, like I alluded in my presentation, is more complex than the far field. The far field is fairly well behaved. The near field is complex. So a lot more work has to be done on near field research to aid better performance in the far field, but even to improve the near field behavior of antennas.
Okay. This is a question from Martin Thorpe. You mentioned terahertz. Would you please say something more about this? Potential applications, presumably it's ionizing.
No, it's not.
It's not.
Okay.
Sorry.
Okay. So let me start by answering the last part of the question, which is that no, terahertz frequencies are non-ionizing. Typical ionizing frequencies are ultraviolet frequencies, so beyond the wavelength or smaller wavelengths than visible light. Typically, it is generally accepted that the energy levels should be about 10 electron volts and beyond of the incoming wave to knock. The whole idea of ionizing is that ionizing radiation ionizes matter. In other words, it has a non-reversible effect on DNA. And yes, like I said, exposure is dangerous, but terahertz frequencies are nowhere near ionizing frequencies. So they're safe in that respect. Now, applications, like I highlighted, are largely for imaging and surveillance. It's still a major research area in the universities, and more applications will come on once we get viable products.
So that's me extending on this. So when you say imaging, are you talking medical imaging type?
Correct. I did mention, yeah, so things like dental imaging of the teeth, because such radio waves can actually pass through clothing, so you can use it to image concealed structures on the body and things like that. So it's an area where you can build scanners to use.
So this question is from Zachary K. Smith. With 5G coming into public use and groups forming condemning its use, saying it is unsafe, how would you argue that it is safe for the general public?
Okay, we must all appreciate the planet we live on. We live on Earth. We are exposed to the sun's radiation. Luckily, we have an atmosphere that takes care of ionizing radiation, and we are left with radiation that is non-ionizing. I would say that radio waves are far below ionizing areas, so the issue of the danger doesn't come into question. What is important here is that we don't have high power radiation, and that's what the mobile phone companies have been mandated to do by industry and governmental bodies, to keep the radiation below 2 watts per kilogram, which is the specific adoption ratio, to make sure it's safe. Like any technology, a lot of research is still ongoing, but as of today, there's nothing to show that 5G radiation is harmful to people.
Okay. So there's a question here by, hold on. Wisdom. How demanding are meta services used for antenna design?
Yes, the meta services, like I said to you, they're now emerging, and they tend to be band limited. So you can use meta services over finite frequency regions. You design them and you use them. So the question now is, what properties are you trying to realize from them? What we use them for an antenna today, antenna work today, is to make very compact low profile structures and to improve the propagation environment or the radiation environment. And those applications that we're seeing a lot of work in that area. But in terms of demanding, it all depends on what demands you place on it. If you ask him for a lot of bandwidth, then maybe you might not be able to get away with the meta surface. So it all depends on the specifications you place on it.
Okay, so this is from DRC. He asks, just to clarify, in tensorial, hold on, I need to think about it. I guess it means in terms of real world measurements as opposed to modeling. There's not really a question here. Sorry, I'll have to skip to the next one. Anonymous attendee, can you provide some reading material on mobile antenna and 5G antenna, please?
I'm afraid I can't point to anything, and I wouldn't want to at this stage. What I would say is you can do a good internet search on Google,
yeah,
but I wouldn't want to.
Yeah, that's it. So this question is by Alex Wood. What is the next big step in antenna research?
Well, very good question. The next big search area in antenna research today is what I highlighted, which is the issue of it's twofold. It's material science. We need new materials to be able to develop new structures, novel structures, and like I highlighted there with metamaterials and with nanomaterials, those areas of interest. The other area of interest is this issue of what I would tend to be orbital angular momentum, where you are trying to provide novel radiation modes for antennas. Those are the two big areas right now in antenna research, and that's where we are. We've pushed the frequencies up to millimeter wave. Frequency increase will keep being pushed, but the big areas are material research, yeah, and wave research. Yeah.
Okay. Hold on. So this is by CISO. Do you think a time will come when wireless communication can be as fast as fiber optic networks?
It's a very good question. And I would say it is possible in the long term. What we see, and there's one thing with guided waves. Guided waves tend to be, with fiber optics, tend to be very low loss. And that has been the push. So it's a guided wave, so the loss to the wave is very low loss. But with a lot of work being done today in what we call space optics, where you're transmitting space optics, we must realize that light is an electromagnetic wave. And once you go into higher frequencies, into the optical frequencies, you are actually working at very high data rates. So the speed is higher because the data rate is higher due to the higher frequency. So if you propagate waves at the speed of light, which people are looking at, yeah, I do. That's possible. Yes, the key is loss, and that we can overcome loss in the future.
So this is from Rob Kira. Could an antenna design ever be developed that could work adequately at all frequencies?
very difficult to do. Very difficult to do because an antenna is a transition structure. And at different frequencies, the wave nature changes. So you need different kits. So it's very difficult to do. I would say you will keep on requiring different transition devices at different frequencies.
So physically, what does it mean? You'd need adaptable materials.
Yes, correct.
Yeah, you'd need physically adapt materials.
You did adapt. Yes, yeah. Exactly. Yeah, and like I said, it depends on the frequency. And the wavelength is important. So at lower frequency, you have longer wavelength, you need a different structure. Higher frequencies, shorter wavelengths, the structure changes. So although we develop broadband antennas, I don't foresee a time where we develop one antenna for the whole band.
Okay. So this question is by Ian Simpson. Sorry. When do you see the technology for optical laser links and terahertz links merging?
Well, I want to emphasize one point here, that terahertz is a long way from optical frequencies. It's a long way. So I don't see that merge anytime soon. I think let's get through making viable devices at terahertz frequencies first.
Okay.
So I don't see that happening anytime soon.
So we shall take 5 more questions, if that's okay with everyone. Is that okay if you, Ernest? Willing to?
Yes, that's fine.
Yeah, so 5 more questions. So, hold on, excuse me. So this is from Francis de Gaulle. Will 5G applications from LEO and MEO satellites act as a competition to land-based 5G in terms of latency and buffering?
Good question. It's that link. There is always going to be. You can't compete with terrestrial links from satellites. There's always going to be that latency because you're propagating through space. So a satellite link will always have that problem. The latency is the distance. But at the same frequency, you have a wider distance to cover. There's a latency problem. For instance, as you know, I mentioned when you're making the communication from Mars here, you're somewhere between 3 and 11 minutes away. So you have to put that in. This is a distance. So 5G on the LEO orbits can improve. And I know that where the question is coming from because you have companies that are trying to build low Earth orbit satellites to do mobile communications now. But you still have to make that factor in. The question now is what latency are we going to live with? And I would say that it may not be so big a problem if you don't notice it. So you're making a phone call and you're speaking, you may not notice the latency that is in the microseconds. So there will be that latency due to distance.
All right, so this is a question by Sava. It's a bit long, so hold on. Considering trains, do you think it is more likely that rolling stock manufacturers and train operating companies will eventually provide better onboard connectivity for the public, or that the signal availability provided for mobile devices across the country improves first? You want me to repeat that?
I think I have of it. I think yes. I think a lot of work is being done in the train sector right now that I'm aware of, and that 5G research in that area is ongoing. So I do feel that you will see improvement in that sector because at least in the UK there is research going on in that area. Yeah, so I'm looking forward to that. Yes.
Okay. So 2 more questions. This is from an anonymous attendee. What are the biggest challenges in ethics that antenna signal developments face?
It's a good question. The engineer has to adhere to ethics, and that's part of the tenets of the IET. Any organization we work with. The ethics are essentially having to articulate what could be of danger to the public. And I alluded to that myself when I talked about radiation hazard requirements. Usually, when you expose any living thing to long, high power radiation, there could be danger. It's important that people who are in this industry, as engineers, highlight those dangers when they work on these problems. So it is the danger to life. It's important that one emphasizes it, and there's no compromise for it.
So I will, one more question, the last question, Harold. So this is from Pradeep Agrawal. Co-site interference is a key issue on platforms. For VHF frequencies, apart from using large Yagi or log periodic antennas, are there any other techniques to achieve directionality?
Well, thank you, Sandeep, for that question. The thing at hand here is that it's a law of physics that a larger aperture at a certain frequency gives you more directionality. And that is what you've alluded to here. You need larger Yagi or larger antenna to achieve that performance. I don't see how you can get away from that. The only thing else you could do is to have shielding. The only thing else you could do is to have shielding in the vicinity you want to shield from. And there are ways of doing that these days. You can shield using radioabsorbing materials or novel high impedance structures, but you can't get away from the fact that the aperture size of an antenna limits the directionality you can have. You can maybe use a lens, but you're still constrained by the aperture you have.
Thanks for that, Ernest. So I'll sneak in one last one for myself, right? I mean, you've been working in antenna design for a while, right? I think I've maybe spoken to you about it. How do you see the current developments and the state of antenna design in general within the industry and in academia?
Like I alluded to in my challenges for antennas, the issue at hand is in the industry today is you need cost-effective designs. So the antenna designer has to be able to design his or her product within that framework of cost. At the same time, you need to meet the specifications of what you're giving. Sometimes people ask for the moon and they can't have the moon. And it's good to point out to people what the expectations are and what can be achieved. And so this discussion you need to keep having, especially with the system engineers on programs, that you meet, you have an agreement on what is achievable with the time and the materials, and of course the cost.
Well, thanks very much, Ernest, for giving us your time today, and thanks for the presentation. It was insightful. As you know, I've been working in radar for a few years now, 20 years, but I guess there was a lot I didn't know about the history of antenna. Maybe I should do some reading, to be quite frank.
Thank you. My pleasure to come here today.
Thanks to everyone who attended and for all the questions. I guess we'll try to maybe answer some of the questions offline later. I don't know in the past. I don't know what the protocol is here at this point. But once again, I'd like to say thank you to Ernest for giving us his time and an insightful talk. Thanks very much, Ernest. And thank you for everyone who attended. Thank you.